Sasa, you can start.
Okay, so we'll start with 2017, then we'll go to 2018 and 2019. So I hope you guys have the problems. I won't read them. Yeah, so we'll start with 2017.3, which is a problem of a function, a polynomial, and yeah, we know that some kind of weird condition holds for this function. So this is the condition. Okay, so let's think about what do we know about this function. Oh yeah, first, so we have to show that there's always exist a real number q such that this does not hold, right? So I think it is pretty natural here to assume the contrary, that no such number q exists, and then so assume that q doesn't exist. Then for any x, we would have this expression on the left and an expression on the right are always equal, since no such q exists, times x px minus 1. Okay, so why is it natural? Because after assuming no such q exists, we get a whole lot of information from such assumption. So we know exactly what form our expression on the left-hand side has. So it is a very powerful assumption. It gives us a lot of information about the function. So now let's look a little bit at what's happening on the right-hand side. So the right-hand side, we have some kind of polynomial. And let's just think, what facts can we say about it? So what derivations can we make? So we just note that, well, since it has a term x plus 2017 in the beginning, then x equals minus 2017 is a root of this. So if we let's just label this guy as qx. So we know that q of minus 2017 is 0. And also let's label the function on the right gx, just for convenience. Okay, so we know that minus 2017 is a root of this polynomial. What else can we say about it? So in this problem, I would say it is a reasonable strategy to just try plugging in some x's, some values of x, and see if we can say anything about the polynomial on the right hand side. So after we plug in x equals 0, then we know the exact value of qx at this point. So for x equals 0, the value of qx will be minus 2017. So it is a good value because we know it is a good value of x because we know the exact value of q x at this point. So q of 0 is equal to minus 2017. Okay, so here's something interesting already. So these two altogether, they mean that q maps 0 to minus 2017, and q maps 0 to minus 2017. So we can write it. We can write the following: that q of 0 is equal to 0. Right? Okay, and this is, and we will also need the following fact, that Q of 0 itself is not equal to 0. Okay, so this is all information that we will need from the right hand side is already here. Spoiler. Now we'll move on and we will see what it means for the left hand side. Well, since we know that left hand side and right hand side are equal, then it also means that G of 0 equals to 0, but G of 0 is not equal to 0. What is G of 0? Since G is f to the power of, composed with itself this number of times, then G of x is just f to the power 2017 to the power 2017 factorial times 2 of x. Okay. So we know that f to the power 2017 to the power of 2017 factorial times 2 of 0 is equal to 0. However, f to the power 2017 factorial without the times 2 of 0 is not equal to 0. Okay. Now let's step back a little bit and let's think about how does this sequence behaves. So x, fx, f, f, x, and so on. Let's just plug in x equals 0 here. So let's start from 0, then we consider f of 0, f of 0, and so on, fn of 0, and so on. So my claim is that if it is periodic, then it is periodic from the if there is if there is 0 somewhere in the sequence, it is periodic. Why? Because next term is completely determined by the previous term. So if we have, let's say we have 0 somewhere in this sequence, then next term would be f of 0 again, and next term would be f of 0 again, and so it is gonna repeat itself. So we know that since we know that 0 appears in this sequence, we know this sequence is periodic. Okay, so let's just set the minimum period to be equal to t. I say minimum because if t is the period of this sequence, then 2t is also period, and 3t is also period. So we want minimum t. So then we know that the fn of x of 0 is equal to 0 is equivalent to t dividing n. Do you guys understand why is this true, or do I need to explain this? Can you write in the chat? If t is a minimum period of this sequence. Okay, I'll just explain it. So suppose there is so one-way implication is quite obvious, because if t divides n, then we're just stepping some number of periods. The amount of steps is equal to some number of periods from the beginning, and we'll obviously have zeros there since t is a period. So this way implication is quite obvious. So this way implication is not as obvious. So suppose there is a m such that fm of 0 is equal to 0, and t does not divide m. Okay, well, what does it really mean? Okay, let's just look at this sequence. So we know that 0 appears once in t terms, because t is a period. So suppose there is also another 0, which is in a position that is not divisible by m. So suppose here at position m, we encounter another 0. Then, since this sequence is periodic with period t, this 0 will appear at position, so if this was position m, it will appear at position m minus t over here. And it will appear at position m minus 2t, since we know that the sequence is periodic. And continuing doing that, we can show that it will appear at position m mod t. Okay? Then m mod t is also a period of this sequence. However, m mod t is less than t, but we assume that t is the least period of this sequence. Okay, so do you guys understand why m mod t is a period in this case? Because if we encounter 0, we showed above that then this distance will be a period of the sequence. It will repeat itself. So m mod t is also a period, but m mod t is less than t, and we assume t is a minimal period. And also because m is not divisible by t, then m mod t is greater than 0. Then it is a valid period, which is less than t. However, we assume t is minimal. So this is not something that can be only applied to this problem. This can be applied to any problem that talks about sequences where the next term completely depends on the previous term, is completely determined by the previous term. Then all these facts about period terms, all of this will be true. So if you knew that before, then you wouldn't have to do it on the contest. You would just apply it. But if you didn't, you could also prove. So yeah, this knowledge can be applied outside of this problem completely. So yes, so now we know that this implication holds. Okay, so what does it mean? We also have these two facts. So we have that f to concatenated with itself some number of times of 0 is not equal to 0. And for this number of concatenations, it is equal to 0. So what does it imply? It implies that our t, period of the sequence, it divides 2 times 2017 to the power 2017 factorial, because this is what our this fact says, that if fn of 0 is equal to 0, then t divides n. So t divides this guy, and because f of f concatenated with itself this number of times of 0 is not equal to 0, that it means that t does not divide this guy. Well, how could this happen? These guys, they're different only by this factor of 2. So it means that it could only happen if this 2 is a reason why t does not divide this guy. And what I mean by that is that the power of 2 that divides t is greater than the power of 2 dividing 2017 to the power 2017 factorial. Do you guys understand why this is true? Could you write in the chat? Sort of. Okay, I'll explain it a bit more detailed. So let's suppose this is p1 to the power alpha 1, p2. Well, we know that one of the divisors is 2, so 2 to the power alpha, p1 to the power alpha 1, dot 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 pk to the power alpha k. Okay, and this guy will be 2 to the power alpha minus 1, because we know that the 2 divides it in the power that is 1 less than the number above. And all other divisors are the same. So we know that t divides this guy. Which implies that t has this form, 2 to the power of b, p1 to the power beta 1, pk to the power beta k, where alpha is greater or equal to b, and alpha I is greater or equal to beta I. So basically, what I'm saying is just that all primes divide t in a degree that is not greater than the degree they divide 2 times 2017 to the power 2017 factorial. Okay. So then let's look at this. So t does not divide this guy. Which means this implies that there is a power, there's a prime in t that divides it in greater power than it divides this guy. However, we already know that all primes, except for 2, they divide it in the powers that are not less than alpha 1, alpha 2, alpha k. So the only prime that could be is 2. So 2 to the power alpha divides t. Okay, because if this is not true, so suppose 2 to the power alpha does not divide t, then beta would be not greater than alpha minus 1, and then t would divide this guy, which cannot happen. Okay, then beta has to be equal to alpha, which means that power of 2 dividing t is equal to power of 2 dividing this number. So, well, what this tells us about t is that t is very big, because the power of 2 dividing this guy is huge. So what is it equal to? Well, because it is factorial, we know how to compute it. So v2 of this guy, 2017 to the power of 2017 factorial is equal to, by the way, v2 is a power of 2 dividing the number, in case you guys are unfamiliar with this notation. So I hope do you guys know how to compute power of prime dividing the factorial? What's the formula for this? Does anyone not know? If you guys not know, then write in the chat. Okay, I don't know. Okay. Step back. I mean, the formula here is actually not needed. We just need, well, we can bound v2 of t just by saying that it's at least 2 to the power number of events in this interval. 1 2017 to the power 2017. Why is that? Because each even, it contributes at least 1 power of 2 to this term. So then, yeah, the power of 2 will be at least number of evens in this interval. Plus 1, actually, because we have an extra 2 in here. So this is equal to, we'll just write that it's greater. So this is greater than 2017 to the power 2017 over 2. So, and this is only the power of 2 dividing t. So then t is at least 2 to the power this guy over 2. So this number is huge. And we know that this is a least period such that we encounter a 0. And it has this length. Yeah, concerning the power of prime dividing factorial. So if we have a n factorial product of numbers 1 to n, and we have a p, and we want to count the power of p dividing n factorial, it has this formula. So this continues until the power of p we're dividing n by exceeds n. So why is this true? I'll briefly explain why this holds. So this is the number of n, number of numbers in the interval from 1 to n that are divisible by p. So they contribute 1 power of p into the sum. Okay, so if we draw like a diagram where x-axis would be numbers from 1 to n, and on y-axis we will capture their power of p that divides them. Okay, some of them will have 0, some will have 1, some will have something else. Anyway, yeah. So what this term is the area of the first row over here. Because the number of squares in the first row is the number of numbers in an interval from 1 to n that are divisible by p. So n over p squared, it would be an area of the second row. It would be a number of squares in the second row. Because if the tower is at least 2 squares high, then the number is divisible by p squared, and so on. So we're slicing it, this diagram, and this is where the sum comes from. So this term, 2017 to the power 2017 by 2, is we just took the first term and we said that our sum is greater than this term. Yeah, and we don't need much. So yeah, okay, let's do it this way, guys. If something's not clear, please write in the chat, or I'm using something you don't know, then please write in the chat and I will either explain it or I'll repeat something one more time. Yeah. Okay, so we have this bound on t. So t is the least period of f such that f of t of 0 is equal to 0. All right. And we know that yeah, okay, let's look at the terms in the sequence. So 0, f of 0, f of 0, and so on. F t minus 1 of 0, and then we have 0 again. So let's label them. Let's label all the terms in this sequence: x1, x2, x3, xt. So first of all, they're distinct, because if we have if one term was repeating, then the sequence would be periodic with a period that is less than t, but we assume that is its minimum period. So they're all distinct. It's first observation. So second observation is that ft of xi is equal to xi. Well, this is just true because t is a period. Okay. Then we know that because t divides 2 times 2017 to the power of 2017 factorial. We know that f to times 2017 to the power of 2017 factorial of xi is equal to xi. Okay, so basically this equation has at least t roots distinct. Okay, now let's remember that f to the power, I mean not to the power, concatenated with itself this number of times of x is equal to q of x, our polynomial. Then this guy is q of x. So q of x equals x has t roots. Yeah, well, what do we know about q? So we knew that p is a non-zero polynomial with degree no more than 2015. So since q is equal to q plus 2017 times q, let's use x. So x plus 2017 x px minus 1. So then we know that since p of x is non-zero, then degree of q would be at least 2. And degree of q is also less or equal to 2017, because degree of px is less than or equal to 2050. So we multiply by x and by x again, which gives us an upper bound of 2017. So okay, well, this equation, so this polynomial then, minus x, it has a degree of qx minus x is less or equal to 2017 squared. However, this equation has t roots. And t is very, very large. So it is greater than 2 to the power of 2017 to the power 2017 over 2. So clearly, this guy is greater than this guy. So if the number of roots is greater than the power, then q of x minus x must be identically equal to 0. Because if it was a non-zero polynomial, then it couldn't have more roots than its degree, but it does. So it is identically 0. So q of x is identically x. However, this is also impossible because degree of q is at least 2. So degree of q of x is at least 4, which is impossible. So we obtained our contradiction. Also, you could guess that our solution will end in some sort of way like that, because well, when the problem states that p is a polynomial and there's a upper bound on its degree, then you will probably need to find um, some, like, a large number of values of this polynomial, and then the polynomial can be restored by its values. So if we were like, if the degree of polynomial is 2017 and we found 2018 values at 2018 points, then the polynomial can be restored. For instance, if a polynomial of degree no more than 2017 has 2018 roots, then it is identically 0. So yeah, if you have some kind of condition like that, it's usually then you can bet your solution will end somehow like this. So yeah, let's just do like a recap of what just happened. Yes, so first of all, we started at investigating right-hand side, and then well, we found out that we can find numerical values of qx at some point. Okay, and so we can find it at point minus 2017, and we can find it at point 0. Oops, sorry. Yeah, and then we applied that knowledge for sorry. We applied that knowledge for the left-hand side. Right, and we investigated. So we investigated a sequence f concatenated with itself n times of 0, and we found out that it has a period, and these two conditions, it made sense to us in light of our divides one of the numbers does not divide the other one, which we use solely to just develop a lower bound for t. So t, we just need to know that t is large enough, and it is large enough. And then because the size of a period is t, then we have t distinct values that function takes at this point. So this equation has many roots. So as this equation has many roots. Yeah, and then we concluded that it is impossible, since the restrictions we have on the degree of p. Okay, so let's move on to number 4. Number 4 is a geo. So, and we have to prove if and only if condition. So we need to prove that. So this is 2017.4. So we know we have some kind of a triangle. We draw its bisectors. Okay, C0. And so we need to prove that this condition is equivalent to this condition. So when you have an equivalence relation like that, it is always a good idea to start with a simpler side. So simpler side, um, for me, it looks like the implication from left to right, because if we know that BAC is 120, we know some facts about the triangle ABC, right? We know one fact for sure, that one of its angles is 120. So it is pretty straightforward to use. That's what I mean. This condition is very not straightforward to use. Okay, so we start off with assuming BAC is 120, and then we'll show that the angle on the right hand side is equal to 90. So let's redraw this. P0, C0. So this angle is supposed to be 90 degrees. Well, when does, so we have some kind of construction like that. So we have A0, we have B, we have C, and there are two lines coming out of A0. I mean to prove that this angle is 90 degrees. So so for me, it involved some kind of intuition, but well, I just thought about, well, when does this happen? So when in geometry, at what situation this number we would tell that this is 90 degrees for sure, if these two lines were bisectors of the angles. So, and you can so this was my initial guess, and to like on the contest to prove it or to disprove it for yourself, you can try writing like some try drawing some precise pictures and then evaluating whether these guys will be bisectors or not. So it turns out that they are. If the BAC is 120, these guys will be the bisectors. And if they're bisectors, then we know automatically that this angle is equal to 90 degrees. So, and this is what we will aim to show. So so there's a lemma for bisector. If A0 is a bisector, then BA0, the ratio of BA0 to A0C is equal to BA to AC. So basically, the bisector divides an opposite side to in the ratio of the sides of a triangle. So, and this is also an equivalence relation. So if it is equivalent to AA0 being a bisector, so if we prove this is true, then we know that AA0 is a bisector. Okay. So this is what we'll try to prove. This is the condition we'll use. So we already know AA0 is a bisector. Then there is a point C0 on the side, and we aim to show that AC0 is a bisector of this angle. Okay, so we aim to show that AC0 over C0B, I'm writing the question marks because we don't know it yet. We just aim to show this. So AA0 over A0B. So the ratio of this is equal to the ratio of these guys. So this is what we aim to show. Well, we know that C0 is not a random point. It is a point where this bisector intersects the opposite side, right? So then we know that AC0 over C0b is equal to AC over BC. All right. Yes, so this is we aim to show that AA0 is equal to A0B times AC over BC. Yeah, so this is what we need to show. Okay, so let's get rid of this guy, A0B. So what is A0B over BC? So again, A0 is not a random point. It is a point where the bisector intersects the side. So then BA0 over BC is going to be AB over AB plus AC. Again, because BA0 to A0C is equal to BA to AC. So again, then we can rewrite this guy as AB times AC over AB plus AC. So in other words, BC over B plus C, which is a pretty neat formula, I would say. So if we show this, then we're done. Because then the ratio would be, so this equality would hold, and this equality would hold, and then AC0 would be a bisector. And then similarly, we could conclude that AB0 is a bisector, and then the angle would be 90 degrees. So we just need to show that the length of a bisector is this. So to be proven, AA0 is equal to BC over B plus C. Okay, so let's label this as L. Now we don't have to, and this we're in a good situation because we don't have to deal with other two bisectors. So now we just know that this angle is 120 degrees, which is equivalent to saying that these two are 60. So these two are 60. And we know that AA0 is a bisector. So what we're gonna do is we're gonna just apply a cosine theorem of triangle for this triangle first, and then for this triangle. Why is this a good idea? Because we know these two sides, and we know the angle in between them. So it is good. It is a good situation to apply the cosine theorem. So then we know that BA0 squared is equal to so AB is C squared plus L squared minus 2CL cosine 60, which is just 1/2. So this would be minus CL. So similarly, A0C squared is equal to B squared plus L squared minus BL. So this is a cosine theorem for this triangle. Okay. And also we know the ratio of these guys because BA0 to A0C is again, it's AB to AC because AA0 is a bisector. So then C squared over B squared is equal to C squared plus L squared minus CL over B squared plus L squared minus BL. Yeah, okay. And now just play with it and then we're gonna get the needed result. B squared L squared minus B squared CL is equal to C squared B squared plus C squared L squared minus BC squared L. So then these two cancel out and then we can divide by L. And yeah, let's just put everything containing L in one side and everything not containing L in the other side. So B squared minus C squared L is equal to B squared C minus BC squared. So both sides can be factored. L is equal to BC, B minus C. So dividing by B minus C, we obtain L equals BC over B plus C, which is exactly what we need. And we showed that it is enough to show that to have our condition. Okay, so now now we have to now we need an implication in the other way. So from the fact that this angle is 90 degrees, we need to conclude that BAC is 120. So the other way is B0, A0, C0 is equal to 90 degrees. Is the first thing we assume, and then we're going to prove BAC is equal to 120. So I told you guys about the lemma that if we have a bisector, then the ratio of sides is equal to, yeah, this one. So no, this one. That the ratio of these segments is equal to the ratio of the sides. So it can be generalized in the following way. So if we have a triangle ABC, now let's make it BAC and D. So if this angle is alpha and this angle is beta, so let's label this phi, and this will be pi minus phi. Then we can write a theorem of sines for these two triangles. So AB over BD is equal to sine phi over sine alpha. And AC over CD similarly, if we write it for this triangle, AC over CD is equal to sine pi minus phi, which is sine phi, over sine beta. So when we if we divide these two, then we get that AB over AC times now let's divide the second by the third by the first one. Okay, then we get AC over AB times BD over CD is equal to sine alpha over sine beta. So this is the lemma. The ratio of sines is equal to the product of these ratios. So if we note that if alpha is equal to beta, i.e. AD is a bisector, then we would have AC over AB equal to CD over BD, which is our lemma for a bisector. So we're going to use this statement for our triangle now. So why do we want to use this statement? Because we know that in triangle ABC, A0, B0, and C0 are foots of bisectors. So we know a lot of ratios on this picture. Okay. So we want to use okay, so let's set this angle to be equal to alpha and this angle to be equal to beta. And then we're going to write our lemma for this triangle. So sine alpha to sine beta is equal to oh yeah, okay. Sine alpha to sine beta is equal to AC0 over C0b times BA0 over AA0. So this is our lemma for the triangle ABA0. Okay, again, this can be expressed as AC over CB because C0 is a foot of the bisector. And then we would get that this guy is equal to, again, BA0 over AA0. So again, and similarly to what we had before, we have this ratio BA0 over CB, which can be expressed as AB over AB plus AC. Okay. So this formula is pretty interesting because, well, we selected alpha and beta to be these angles, and these angles, they favor point B over point C, but the formula is symmetric with respect to B and C. So it means that if we consider this angle and this angle, which we know is equal to, this one is equal to 90 minus alpha, and therefore this equals to 90 minus beta. So we will get the exact same formula because if the obtained formula is symmetric with respect to B and C. So then we get sine of 90 minus alpha over sine of 90 minus beta is equal to sine alpha over sine beta. Okay, so this is just cosine alpha over cosine beta is equal to sine alpha over sine beta. So rearranging this, we get tan alpha equals tan beta. And well, the way tangent, even, no, let's, if we rearrange it differently, we'll get cotangent alpha equals cotangent beta. So if we look at how cotangent behaves on 0 to pi, it looks like this. So it means that if two angles are from 0 to pi and they have equal cotangents, that these angles are equal. So alpha is equal to beta. So well, this implies that this guy is just 1 because this is sine alpha over sine beta. So we know that this guy is just equal to 1, which means that AA0 is equal to AB times AC, AB plus AC. Which we've shown earlier is equivalent to angle BAC being equal to 120 degrees. Yep. Was that clear? So yeah, this problem is a bit formulas heavy, but well, the intuition behind this is that if we have a lot of bisectors in the picture, then we know a lot of ratios in the picture. So ratios is probably something we want to deal with. We want to be dealing with. Yes, and so you guys should definitely, if you don't already know and remember this lemma, and this lemma about the ratio of sines, I don't remember how it sounds. I just remember this ratio exists and it's pretty nice. And if I want it in the contest, I just derive it. Because it is not easy. You just write two sines theorems and then you divide one by another. So yeah. Okay. So this was 2017. All right. So let's move on to 2018. So number 3 is a probability problem. So 2018.3. Yeah, if you guys missed something or didn't catch something in the last solution, please feel free to unmute yourself or type in the chat and I will go back and I'll explain it again. So yeah, 2018.3 is a probability problem. So we're asked a question. So we have a circle, endpoints are randomly placed on it, and we have to figure out what is the probability that the origin of the circle is contained in inside this n-gon. So suppose it has a probability p. So my claim is that it is easier to compute 1 minus p. Why? So 1 minus p is the probability that the origin is not contained inside this n-gon. So maybe it looks somewhat like this. So just, well, if you have a problem, you have to compute something, compute some kind of probability. It is, you have equal opportunities. You can compute P or you can compute 1 minus P. Just for me personally, when I look at this picture, 1 minus P, I can come up with a, like a criteria or an explanation of what does it mean that what does it mean that the center is not contained inside of this n-gon. So first of all, it means that there exists one like a diameter such that the n-gon is completely on the one side of it. Or equivalently, you can say that if you pick along a side, then the polygon is completely on the one side of it. The diameter? Yeah, so anything passing through the origin, any line is the diameter. So the fact that n-gon does not contain the origin is equivalent to the fact that there exists a diameter, like we can pick this diameter. It is not unique, obviously, but there exists a diameter such that this n-gon is on the one side of it. So 1 minus P is when the n-gon is all on one side of the circle. Yeah, sort of. But we don't know, like the problem is we don't know which diameter to pick. Because it can be positioned like in this way, right? So, and then this diameter wouldn't work. Then we have to pick a horizontal one. So this is the problem. This means that all points have to be within, yeah, exactly. So it means that all points have to be within a 180-degree arc. Yes, exactly. So, but it is not clear, the complication of this problem is that it is not clear which 180 arc it would be. Okay. So what I'm gonna do here is I'm gonna introduce a function of polynomial. So let's consider a polynomial. And consider diameters that pass, all diameters that pass through its vertices. So if polygon does not contain the origin, yeah, let's call the diameter good if the polygon is completely on the one side of it. If n-gon does not contain the origin, then it has two good diameters. Which those would be? Well, those would be these ones. So first and the last point on this arc. would be the ones that have that are good diameters. All other ones would be bad because they will be points on the one side of it and on the other side of it as well. Okay, what if polygon contains the origin within itself? My claim is that it will have 0 good diameters because every diameter passing through the origin, if all points were on the one side of it, for example here, then the polynomial wouldn't contain the origin within itself. So all of them will be bad diameters. So 0 good diameters. So it turns out that if you take a polygon P, and f of P would be the number of good diameters, then f of P is equal to 2 it's okay. If and only if P does not contain origin, and fp is equal to 0 if P contains origin. Okay, so this is good because now we have a strict criteria for polynomial whether it contains the origin or it does not contain the origin. We have this criteria is very strict because we have a function and we have the values defined. So what is the expectation of f of p? My claim is that it's 2, 1 minus p. So fp is a number of good diameters. We know it is equal to 2 if p does not contain u, which happens with probability 1 minus p, and it equals to 0 if p contains origin, which happens with probability p. So the expectation of fp is equal to 2 1 minus p. So now if we determine the expectation, we can compute the probability. Okay, so and what we're gonna do now is this is a common method in the when you apply probability to combinatorics, is called a method of indicators. So we have endpoints. So if we draw an arbitrary diameter, it is either good or bad. So through point A. So let's call mu of A is 1 if A is good. And mu of A is equal to 0 if A is bad. So diameter through A is bad. So the way expectation works is that expectation of sum is equal to sum of expectations, always. Okay, so then expectation of f is equal to expectation of mu of a1 plus expectations of mu of A2 plus dot 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 expectation of mu of AN. So because A1, A2, AN are symmetrical, these guys, all these guys would be equal to the same value. So this is just going to be equal to M E of mu, let's say A1. So now to get expectation of F, we just need to compute this guy and we're done. And this guy is fairly easy. So here's why. Because first we place A1. Actually, we can expand it even further. So because mu is an indicator, then its expected value is the probability that diameter through A is good. So probability that dA1 is good. Because remember how we defined it? Mu of A is 1 if it's good, which happens with the probability that diameter is good, and mu of A is 0 if A is bad, which happens with a probability that diameter through A is bad. So the expected value would be 1 times P plus 0 times 1 minus P. So it is N times the probability that the diameter is good. So now we just have to compute this and we will be done. And this is fairly easy. So let's draw our diameter. And now, what is the probability that all points will end up on the one side? Well, it is equal to 1 over 2 to the power n minus 2. Because now it's very easy because the circle is split in half by one particular diameter. And then, so the probability that all points will end up here is 1 over 2 to the power n minus 1. Probability that all points will end up on this side is 1 over 2 to the power n minus 1. So the total probability will be the sum. So 1 over 2 to the power n minus 2. Okay, why? Because the probability that particular point will end up here is 1/2, and that it will end up here is 1/2. Then the probability that all points will end up on the right is a product of n minus 1 1/2, is 1 over 2 to the power n minus 1. And the same for the left side. So the total number, the total probability will be equal to this. All right, now we're done. So we know that expectation of f, which was equal to 2 times 1 minus p, is equal to n over 2 to the power n minus 2. So then 1 minus p is equal to n over 2 to the power n minus 1. So p is equal to this. So we're done. Okay, so this is a quite tricky probability problem. So first of all, we need some kind of criteria for a polynomial, for polygon being on on the containing origin or not containing origin, because this is a vague condition. We cannot express it in like some kind of formula or like some kind of mathematical expression. So we need to formalize it, right? And the way we formalize it is that by coming up with these good diameters and bad diameters. Okay, so and we introduce a function of polynomial that is equal to, we prove that it is equal to 2 if P does not contain origin and contains and 0 if P contains origin, right? And then we computed its expectation first using the P that we need to find, and second using the law that the sum of expectation is equal to expectation of a sum. So why do I like this function f? Because it can be decomposed into n smaller functions, and each of them is basically the same thing. So if we want to compute the expectation of f, this would be just n times expectation of the smaller function. And the expectation of a smaller function is fairly easy to compute. So we can find P finally. Okay. Fascinating. Yeah, let's move on to number 4. Okay. Number 4 is about a sequence, which is considered mod 2018. So we know that Sn is equal to C Sn minus 1 plus D Sn minus 2. So then n is given. So this probably doesn't really, the exact expression doesn't really matter. It just matters that it is very, very big. Okay, and so we need to prove that T of n is equal to T of 2n. Or equivalently, that Sn mod 2018 is equal to S2n. Regardless of choices A, B, C, and D. So again, this is something, this is a problem about periodic sequences. However, in this case, we have the next term is determined by 2 previous terms. Okay, so Tn is determined as Ctn minus 1 plus Dtn minus 2 mod 2018. So let's consider following numbers. Let's consider T0, or does it start with the index 1? Yeah, it does start with index 1. So let's consider following pairs: T1, T2, T2, T3, T3, T4, and so on. Tn minus 1, Tn. No, let's make it Tn plus 1. So what are the possible values for T? T is a remainder, mod 2018. Therefore, T can be from 0 to 2017. And T2 can be from 0 to 2017. So there are, for a pair XY, there are 2018 squared possible choices. All right. Then if we take n is equal to 2018 squared plus 1, there will be at least 2018 squared plus 1 pairs, and there are 2018 squared possible values that those pairs can take. Therefore, by pigeonhole principle, we will have two pairs that will end up being identical. So suppose this one and this one are identical. Okay. So if they're identical, I claim that the distance between them is a period of the sequence. Why? Well, suppose tk plus 1 is equal to tm plus 1. How does tk plus 2 determined? It is determined by combining ctk and dtk plus 1. So similarly, tm plus 1 is combined by obtained by combining these guys together. So because tk is equal to tm and tk plus 1 is equal to tm plus 1, then tk plus 2 is equal to tm plus 2, and so on. So that because the next number is determined by the previous two, if at some point these will happen to be equal, then starting this position, starting the position number k, the sequence is periodic with a period t. Okay. Sounds good. So, and m minus k would be a period. So now we know that our sequence is periodic. Starting from some point, it will be periodic. We also know that our so t is less or equal to 2018 squared plus 1 minus 1 equals 2018 squared. Okay, so let's look at Tn and T2n. So these guys, the distance between them is n, and n is 2018 squared factorial. So we know that t is in between 0 and 2018 square, 2018 squared. Then for sure t divides n. Therefore, Tn is equal to T2n because they're separated by some number of consecutive periods, right? So no matter what ABCD we choose, this will hold always because the sequence is periodic, and we showed that the period is less than 2018 squared. So then Tn would be always equal to T2n. A little remark. So we notice here that the sequence doesn't have to be periodic from the beginning. So it can happen to be something like 0, 1, 2, 3, 2, 3, 2, 3, 2, 3. So this sequence is periodic not from the beginning. It is periodic from the position number 3. But it doesn't matter because if sequence is periodic starting with kth position, then k is less than 2018 squared. So this number, Tn, is definitely after the sequence started being periodic. So then Tn equals T to n. Okay, so this is just another problem involving periodic sequences. But this time, the next term is determined by two previous ones. And because t doesn't have a lot of possible values, then we can estimate the value of its period. It is less or equal than 2018 squared. Then it for sure it divides n, and we win, basically. Okay, so this was 2018 tiebreaker. Now let's move on to 2019. So number 3, unfortunately, I haven't figured it out. I had some ideas with generating functions. So this, for me, it looks very similar to the Catalan numbers, but like in 2D. So I tried to come up with a recurrent formula for number of ways to do it, and consider a generating function of two variables, but it didn't work. So yeah, if I figure it out in the future, I will probably let you guys know, and maybe yeah, maybe I'll send Meng the solution or something. Yeah, anyway, but for I have figured it out. So okay. Number 4. (2019.4). So this one tells us that c squared f of x plus y is equal to fx fy. And we also know f of 1 is equal to c. Okay, so this to me, it looks terribly similar to what's called a Cauchy equation, a Cauchy functional equation. So it is a very famous thing. You can Google it. It's on Wikipedia and stuff. So this functional equation, it tells us to find all functions for which this is true. Or there are some variations where we have to find all functions such that this is true, or all functions such that this is true, or even all functions such that this is true. Wait, so no, I meant to write product here. So f of sum or product equal to sum of f's or the product of f's. It's a family of Cauchy functional equations. It doesn't matter which you choose. So they all have similar approaches to solve them. So I will just choose first one. So moral of the story is that this functional equation cannot be solved. There's no you cannot show, for example, that f is continuous. So there is a lot of families of discontinuous functions that satisfy this equation, and they look very, very, very weird. So like an obvious solution would be c times x, but there are many, many other solutions that look very weird. So if you guys know what the Hamel basis is, so it is a basis of real numbers. We define f in each point of this basis, and then the function obtained will satisfy our Cauchy functional equation. But yeah, this is not what we want. So moral of the story is, to solve this, we need some kind of additional condition. So we can solve it if we know that f is increasing, or f is continuous. In either way. And so the strategy for solution would be that, well, first we figure out values at integer points. Then we figure out values at rational points. And this can be done, so you can actually prove that if f of x plus y is equal to fx plus fy, then f of p over q is equal to p over q f1, which is a lot. So if f is none of these, then we can't go anywhere from here. However, if f is continuous, for instance, if f is continuous, then we know that limit of if x approaches c of fx is equal to fc. So let's take an irrational number and let's approach it with a sequence of rational numbers. So if we take we want to figure out a value at irrational point, so fr, we know it is equal to fx approaches r. Yeah, fx when x approaches r. So if we take x to be rational every time, so we approach it with a sequence of rational numbers. Any real point can be approached with a sequence of rational numbers because rational numbers are dense. Then at any point, this fx would be equal to r f1. And this limit is very easy. So it's just x f1. So we can prove that r f1, I meant. Yeah, so this limit is very easy. We can prove that fr is equal to r f1. Okay, so this is a case where f is continuous. So if f is increasing or equivalently decreasing, again, we have f of pq equals p over q f1. So now we want to consider some irrational points, and we will bound it from both sides by a sequence of by sequences of rational numbers. So ai, how should I call it? Yeah, ai is a sequence of rational numbers and bi is a sequence of rational numbers, and these sequence will approach r at infinity. So then, because f of increasing, then f of ai, I mean, is greater or equal to fr is greater or equal to f of bi. So then ai f1 is greater or equal to fr is greater or equal to bi f1. So because ai and bi at infinity, they approach the same point r, then this is a famous theorem in calculus that if we have three sequences and one is bounded between two other ones, and the two bounding sequences approach the same number, then the middle sequence also approaches the same number. Therefore, fr is equal to rf1, because this is the limit of these two, and the fr is bounded between them. Okay, so this is how we solve Cauchy equation. So we're going to apply the exact same strategy for our case. So this looks like This looks like a second equation from the family of Cauchy functional equations, but with a c squared added. So it doesn't really make a difference. Yeah, I'm gonna show you guys all process of solving it. So but if you see something in the future, you should first thing you should think about is a Cauchy functional equation. And if you have a, like, suppose you have a this equation and some kind of condition, then you would probably want to prove that f is continuous or increasing or decreasing, and because this is how you will solve it. Okay, so first of all, we know that f1 is equal to c. So let's plug in x equals 1, y is equal to 0. Then x squared times c is equal to c times f of 0. So because c is, we know that c is greater than 0, so we can divide by c. So c squared is equal to f0. All right. So now let's try to figure out values at all integer points. So let's plug in x equals n, y equals 1. What does it give us? It gives us, where n is integer, it gives us c squared f of n plus 1 is equal to fn times c, which is equivalent to fn plus 1 is equal to fn over c. So from this, this is a recurrent relation, a pretty easy one. So basically, this is it's a recurrent relation corresponding to a geometric sequence. So we know every time n increases by 1, fn decreases by in c times. So then fn, it would be f0 divided by c to the power of n. f0 we know is 2, so this is c2 minus n. Okay, so this works for n non-negative. Now for negative n, we can so this is equivalent to saying fn minus 1 is equal to cfn. So now we have a recurrent relation that goes down, that every time n decreases by 1, the value of f increases by c. So then for f of minus n is equal to c to the power of n f0. Okay, so which is c2 plus n. So then fn is equal to c to the power 2 minus n for all n integer. Okay, I hope this is clear how we obtain this. So now we have values at all integer points. We're gonna figure out the rational points now. So we have this formula. So we want to generalize it for n variables. So let's consider f of x1 plus x2 plus x, let's say n. So first of all, it is equal to f of x1 times f of the rest over c squared. So this can be expanded in a similar way, and we will get f of x1 times f of x2 times f of the rest over c to the power 4. So at the end, we will have f x1, f x2, f xk times c to the power minus 2 times k minus 1. So we just generalized our formula for n variables. Okay, so let's plug in for this is n. We had n variables, not k. So yeah, we just generalized our formula for n variables. So let's plug in x1 equals x2 equals xn equals 1 over n. Then f of their sum will be 1. It is equal to f of 1 minus n to the power of n c minus 2 times n minus 1. So f of 1 is equal to c. Then f 1 over n to the power of n is equal to c to the power of 2n minus 1. Okay. This is the last one. I think we'll be done by 2. Yeah. Okay. So now we really want to take the nth root, but not so fast, because we're not sure if n is even, then it will have like f can be positive and f can be negative. So we have to figure out the sign of f at first. So we know that f squared f of x plus y is equal to fx fy. So then this follows, right? Because x over 2 plus x over 2 is equal to is equal to x. Then this follows. We know that this guy is positive, this guy is positive, and this guy must be positive. So fx is greater or equal to 0 for all x's. Then we can take a root here, root of nth degree. So here we get f of 1 over n equals c 2 to the power of 1 over n. So now you kind of see like the function that we're going to get probably. So this function is probably the solution. We don't know it yet, but we'll aim to prove it. So now we know that what f of 1 over n is equal to where n is integer. Okay, so let's plug in x1 equals x2 equals xn equals 1 over m now instead of 1 over n. Then on the left hand side we will get f of m over n over m, and so f of, because there are n terms and each of them is 1 over m, and we get f of n over m is equal to So there will be n terms, each of them is 1 over m to the power of n, and c minus 2 n minus 1. So we already know what this guy is equal to, right? So then f of n over m is equal to c 2 minus 1 over m to the power of n times c minus 2 n minus 1, which is equal to c 2n minus n over m times c minus 2n plus 2. So these two cancel out, so we get 2 minus n over m. So what just happened is that we now know a value at any rational point. So for any r in Q, f of r is equal to c 2 minus r. Okay, so now, but we need all reals. We only know rationals. So to figure out irrationals, we're going to use the continuity of our function. Note that we never used continuity of the function up until this point. So yeah, even if we were not given the continuity, this would be true. So for rationals, we would get this formula, c to the power 2 minus r. So now we want to figure it out for irrationals. So suppose t is an irrational number. Then there's a sequence of rationals approaching it. R1, R2, Rk approaches t as k approaches infinity. So a sequence of rationals can approximate any real number because rationals are dense in real numbers. So then we get f of t is equal to because the function is continuous, then the value at a point is equal to the limit of this sequence as k approaches infinity, because rk approaches t and f is continuous. So because every rk is a rational point, we know the value of it. So this would be c 2 minus rk. So now what? Well, we know that c to the power x is a continuous function if c is greater than 0, which is the case. Then we can write that this limit is equal to this limit as k approaches infinity, which is equal to just c to the power 2 minus t, because rk approaches t. If x is a rational number or a irrational number, we get that f of x is equal to c to the power 2 minus x. Yep, so this is it. Yeah, do you guys have any questions? Uh, anything you want me to go over again? Okay, if everything was clear, then I guess I'm done. Oh, Mang's not here. Then I guess you guys are free to go. Okay.